In this video, we learn about predicting the physical properties of alkanes, including evaluation of their relative polarities, their solubility in water, their density, and their phase. And one of the things that we will evaluate here when we think about the phase, meaning are they solids, liquids, or gases, and what are their relative boiling points or melting points, is that will allow us to discuss and understand why is it the case that propane, the common cooking gas for grilling, is a gas at standard temperature and pressure, whereas gasoline that we fuel our vehicles with is instead a liquid. Both of those are alkane molecules. Why is one of them a gas and one of them is a liquid? That relates to the physical properties of these molecules, and we will learn about that as we go through this unit. Let's get started and outline some of the key physical properties of alkanes. Well, remember that a physical property is a property that is measurable, such as the polarity of a substance, its density, its phase, meaning solid, liquid, or gas, and those types of features. With regard to the physical properties of alkanes are the least polar, in other words, the most nonpolar, of the different functional groups. So alkanes very noteworthy for their very, very dramatic lack of polarity. Why are they nonpolar? When we talk about polarity, what we're referring to is the difference in electronegativity between different atoms that are found within the structure. And in the case of carbon and hydrogen have a very small difference in electronegativity between those two atoms. And it's only carbons and hydrogens that are present in alkane molecules. And so as a result of the fact that there's very little difference in the electronegativity between carbon and hydrogen, that makes the molecules as a whole very nonpolar. Polar molecules, on the other hand, would refer to structures where there is a considerably larger difference in electronegativity between the atoms that are found there, such as if you have a carbon directly bonded to a halogen, halogens are at the far right-hand side of the periodic table, so they are very electronegative, and hence they would polarize that bond between carbon and the halogen by pulling electron density toward themselves and away from the carbon atom, creating a polarized bond. But instead, carbons and hydrogen have a small difference in electronegativity, so in other words, the electrons are relatively evenly shared between the carbons and hydrogens, and as a consequence, the bond that connects carbons and carbons and carbons and hydrogens is not polarized at all, or polarized very, very little. So if we have a carbon-hydrogen bond, there is very, very low polarity. In other words, there's approximately equal sharing of electrons of the covalent bond that connects the carbon to hydrogen. On the other hand, if we have carbon bonded to fluorine, fluorine is much more electronegative. And so, due to the fact that fluorine is much more electronegative, which I put in as E-neg, electronegative, than carbon, what will happen is that this bond will be very polarized, with the fluorine taking the lion's share of the electron density from this covalent bond. In other words, just because the line drawn there indicating the electrons are shared doesn't mean that's an equal partnership. Instead, fluorine is the electron hog, making fluorine negatively polarized because electrons contribute negativity, and carbon, as a result, having an electron deficiency, making that positively polarized and hence contributing to the polarity of the molecule as a whole. So in the case of structures that are strictly alkanes that don't have any other functional group present, they are very, very nonpolar. The same argument can be made for alkenes and alkynes, that due to the fact that the carbons and hydrogens in those hydrocarbons have very little difference in electronegativity, those molecules are also very, very nonpolar. And that has implications for the solubility of these structures in water. And that's very, very biologically relevant and relevant toward nutrition, because we think of fat molecules as being rich in alkane groups and alkene groups. And that's why fats are not going to be soluble in water, because when thinking about water solubility, the general phrase is like dissolves like. Substances that have similar polarity are going to be soluble in one another. So since water is very polar due to the fact that there's a large electronegativity difference between oxygen and hydrogen, and also that structure is capable of hydrogen bonding to further enhance the polarity. And on the other hand, alkenes and alkynes, are very, very nonpolar at the opposite end of the spectrum. Alkanes are not soluble in water. We'll find that alcohol functional groups that have an OH and have a short carbon chain attached to that, like methanol with one carbon attached to an OH group, or ethanol with two carbons attached to an OH group, are water soluble because that OH group makes those structures polar. On the other hand, alkanes, alkenes, and alkynes, definitely expect those to be insoluble in water, and that's an explanation for why fats do not solubilize in water. Additionally, alkanes, alkenes, and alkynes are also, when we think about density, less dense than water. And so as a consequence, they will float atop water. And that's the reason why if you mix oil with water, the oil doesn't dissolve in the water, but instead it floats on top, because hydrocarbons in general, and we're focusing this discussion on alkanes, are less dense than water. And the density of water does relate very much to the fact that water hydrogen bonds in is very polar, so has very strong interactions between molecules that make them stick very, very tightly together, is the way that you could think of it, making them quite dense. We can also think about, when talking about physical properties of alkanes and hydrocarbons in general, we can think about the phase of those. Phase refers to whether a substance is present as solid, liquid, or gas, and we'll assume that we're talking about phase here at the standard room temperature and standard pressure conditions. So with alkanes, at so-called standard temperature and pressure, STP for short, standard temperature and pressure, what we will find is that alkanes will generally follow this guideline approximately, where alkanes with a total of 1 to 4 carbons will be present at standard room temperature and pressure as gases. And this is why propane, which has 3 carbon atoms and is cooking gas, is a gas and stored in a gas cylinder and quite flammable, of course. If they have 5 to 17 carbons, generally the substance is found in a liquid state at standard temperature and pressure. That is why gasoline is a liquid. Gasoline is enriched in octane. For example, when you see the 87 on the gasoline, or 89 or 91 or 93, whatever you choose, that is an octane rating. And octane is, of course, an 8-carbon alkane. Filling into that region of 5 to 17 carbons makes it a liquid. And then substances that have 18 or more carbon atoms in the alkane chain are generally waxy solids. So an example of this would be such things as Vaseline is enriched in alkanes and is a waxy solid because it has very long chain alkanes within it. So the general trend here, when we think about phase and we try to relate whether a substance is a solid, liquid, or a gas to other properties, is that with regard to this, the more carbon atoms, and I'll put this in as a rule for the phase here, when you increase the number of carbons in your alkane, you increase the melting point, MP, and you increase the boiling point, BP. And the reason for that is that, so I'm going to put BC for because, increase the number of carbons increases the intermolecular forces. Inter means between different molecules. And so when you have millions and millions of alkane molecules in a container, the interaction between those alkane molecules is what we refer to as the intermolecular force. So let's draw this out as a schematic here. If hypothetically I had a container of pentane, so there's one pentane molecule, here's another, they engage in interactions with one another. So intermolecular interactions, I'll illustrate with dots here to indicate that these structures are associating with one another. In other words, they're engaging in intermolecular forces. And if you have a structure like these, pentanes, there is more opportunity for those molecules to engage in these types of interactions than if instead you had only a 2-carbon chain or just had 1 carbon. There are more carbons and hydrogens along here to interact. In other words, more points or locations for these interactions, and that increases the intermolecular interaction that holds the molecules together. And you have to break that intermolecular interaction to melt the substance and to boil the substance. And so the stronger that interaction, the harder it is to melt or boil the substance, because those interactions have to be broken when you are melting or boiling. And so this brings an important implication about melting point and boiling point, which has some strong applications in the field of food, which is that for alkanes that have the same number of carbon atoms, branching is going to decrease the intermolecular interactions. And when you decrease intermolecular interactions, you decrease the melting point and boiling point. So let's write that down as another rule here. And the rule is that for alkanes with the same number of carbon atoms, branching, meaning rather than having a straight chain of carbons, but instead having some of those as a branch, branching will decrease the melting point and decrease the boiling point. And this is an important consideration for whether fats exist as liquids or solids in the body, because if you're looking at a branched chain fat molecule, that branched chain fat molecule is going to have a lower melting point and lower boiling point, hence it's more likely to exist as a liquid. We can put up a specific scenario of this to give you some idea about the impact of branching on boiling point. Hexane, for example, just a straight 6-carbon chain, 1, 2, 3, 4, 5, 6, has a boiling point of 69 degrees Celsius. On the other hand, 2,2-dimethylbutane, so I'm drawing my 4-carbon chain with the 2,2-methyl group, also has the same formula, that is C6H14 in both cases. But instead, with the extra branching that we observe for our branched molecule 2,2-dimethylbutane, the boiling point for that drops to about 50 degrees Celsius. So we notice a 19-degree change in boiling point in response to having 2 of those carbon atoms not as part of the chain, but instead coming off as branches. Because when we have these structures that have the branches, the molecules aren't able to pack as tightly, meaning they have reduced intermolecular forces, allowing them to more easily dissociate and break away, which is necessary to go from solid to liquid and from liquid to gas. As we continue into later units, we will look at the physical properties of a variety of other functional groups as well to evaluate their relative polarity in comparison to alkanes, their density, and their phase to understand how different types of molecules interact with one another and what implications that has for the roles that these molecules play in human health and nutrition.